Hi, I'm Kuba. Welcome back to Basic Anatomy. Last episode we built flash attention kernel in Triton. This time we are going to move to the next part of the decoder layer, feed-forward network. We'll implement fused SwiGLU kernel in Triton. Let's get into it. Look at the Swish-gated linear unit architecture. There are two parallel projections from the input. One is called the gated projection, the other the up projection. Both take the same input x. The gate output gets passed through the SiLU activation, Swish. Then you multiply the gate output and the up output together element-wise. That's the gating part. The gate decides which features from the up projection actually pass through. Finally, there is down projection, which compares everything back to the hidden dimension. Why does gating help? The model learns to suppress irrelevant features per input. For a given token, only the useful dimensions of the intermediate representation survive to the down projection. It's a learned input-dependent feature filter. Here is naive approach. You call three separate operations. Compute the gate projection, compute the up projection, and then apply SwiGLU. Watch what happens in the hardware. The first kernel reads x from HBM, multiplies x by wgate, and writes the result back to HBM. The second kernel reads x from HBM again, same data, second trip, computes x by w up, and writes back. The third kernel reads both intermediate results from HBM, applies SiLU and the element-wise multiply, writes the final output. That's 7 memory transfers total. You are paying for the 5 unnecessary round trips to main memory just to communicate between kernels. The fused approach, one kernel reads x once from HBM, computes both projections, applies SwiGLU in registers, and writes the final result. 2 memory transfers. Read x, write the output. Everything in between stays in fast on-chip memory. This is the key insight. The SwiGLU math itself is cheap. The bottleneck is memory bandwidth, not arithmetic. Removing those intermediate HBM round trips is where the speedup comes from. Now let's look at the actual code. We have 3 input pointers, x, wgate, wup, plus the output. Dimensions m, n, k for the matrix shapes. Strides and 4 tile size constants. Block m, block n, block k, and group M for Swizzling. This block of code calculates our row and column coordinates. It looks a bit heavy, but all it really does is change the order in which we process the output matrix. Let's see why we need it. Normally, Triton processes blocks row by row. And what is the problem? Every time we move to the next block, we have to fetch a brand new column of weights from the slow main memory, HBM. That's zero reuse and terrible performance. Swizzling changes the path. Instead of going in a straight line, we process blocks in groups. Why? Because all programs in that group need the exact same column of weights. The first program loads it from HBM, and the other just grabs it instantly from the fast L2 cache. Then we compute the row and column indices. And we build 3 pointer arrays, one for x, one for wgate, and one for wup. 2 float32 accumulators live in registers for the full duration of the loop, one for each matmul. Each iteration load the one tile of x and reuse in both TL calls. One load, 2 matrix multiplications. That's the fused part. Finally, we advance all 3 pointers to the next tile along the k dimension. After the loop, accumulator gate and accumulator up hold the complete multiple results for this tile, still in registers. We apply SwiGLU right there, where we have SiLU applied element-wise to every value in gate tile. Look at the SiLU activation function. Then we multiply by accumulator up. One line entirely in registers, no memory traffic at all. Then TL_store casts back to the output dtype and writes to HBM. This is the only one write to HBM in the entire kernel. The gate and up projections were intermediate values that never touched main memory at all. I ran this on my RTX 4060 using BLX config. Hidden size 1536 and intermediate size 8960. We have three competitors: our Triton fused kernel, PyTorch with torch.compile, and plain unfused PyTorch. At small sequence lengths, they are really close, but as we scale up, Triton pulls ahead and hits 45 teraflops, while compiled PyTorch sits at 40 and Unfused trails at 37. Notice what Unfused PyTorch does at the right side of the chart. It doesn't flatline, it slowly drops. The second chart sweeps the intermediate size from 1024 all the way to about 14,000. The interesting thing here is that the gap is actually largest at small intermediate sizes. At 1024, Triton leads by 30%. As the matrices get wider, everyone climbs together, and the lead settles at a steady 15%. As always, the code is on GitHub. The kernel, the benchmark, everything. Run it on your own GPU and see what numbers you get. Now we have all required pieces: rope, RMS norm, flash attention, SwiGLU. Next episode we are going to build a complete decoder layer. If you don't want to miss it, please subscribe. Thanks for watching and see you next time. Bye!